Okay, by way of review, I'd like to give you a few little pointers on how to handle circuit components in series and parallel. So first, and this is actually much simpler than you may think it is. It all fits together very nicely. So let's define what we're talking about here. In series, you have components that are linked together end to end like this. So that if there's current, the current has to flow through all of them. And if there's charge exchanged, they can only exchange it with each other. They're not getting it from an outside source, except for the guys on the ends. Okay, so that's series. And so what do we know is true in series? Well, one thing we know is true is if you have a current, so I'm going to write my current like that. If you have a current coming in here and it's flowing in, then it has to flow, the same current has to flow through this guy as through this guy as it flows out the end. So these all have I current. All the components in series will have the same current, and if they're capacitors, they'll have the same charge. Okay, so in series we have the same current, or for capacitors we have the same charge. And I'll explain why the same charge for capacitors in a second if you don't remember that. That gets a little tricky. But what I want to show you is just get the overall picture here first. So let's look at voltage now. Voltage, remember, is the difference between the electric potential at the end and at the beginning. Okay, so here's our beginning electric potential, our end electric potential. The difference is the voltage change across the entire thing. Now, one way to think of this is voltage, and this is sort of an analogy that I hope you remember from our previous unit. Voltage, or electric potential, is like the height of a hill. Okay, the higher up you are on the hill, the easier it is to go downhill, and the more energy you can pick up by going downhill. If you look at the difference in height between two locations, you can see how much energy you can pick up going from one to the other. So you can think of voltage as being like the height of, or the altitude of different points on a road going down a mountain. So here is near the top of the mountain, and as you go down, your voltage decreases. You're going down the mountain, down the mountain, down the mountain. Okay, and the total height change is like the total voltage change as you go down. And this arrow we've seen before points toward higher voltage. Whenever you have an arrow like that, it points toward higher voltage. Okay, now here is the voltage change. Actually, let me just, to be consistent, let me do it like that and leave a little gap so I can write. This is the voltage change across the second component. I'm calling it the second because it's the second one that the current goes through. Voltage change across the second component, and here's the voltage change across the first component. Okay, so if I call this V12, I'm going to call the overall voltage V12. Excuse me, I'm picking the cat up. She's being pushy. Okay, so now she's in my lap, and now she's going to walk around on the desk. Great. Okay, so the way you can look at it then is the voltage change from 1 to 2 is the voltage change across 1 plus the voltage change across 2. I shouldn't call it the voltage change from 1 to 2. I'm sorry, that's incorrect. What I mean is it's the voltage change across the pair. So it's like the total elevation change from this point to this point. From this point to this point is the same as the elevation change from this point to this point, plus the additional elevation change as you go from this point down to this point. Okay, so the other equation, or the other factor here, is that V1 plus V2 equals V12. Okay, and what that means is the voltage is split across components in series. Okay, in parallel, let's look at the other side of things. In parallel, here's our two generic circuit components in parallel. Whatever and whatever. Okay, so when you have current going through, you have the initial current here, but then when it gets to this point, so it's going through this wire, when it gets to this point, it can go either way, and in fact it splits, and so what you get is some current this way and some current this way, and it goes through these guys, and then it re-merges here. There we go, and comes out the end. So if I call this initial current I12, and that's going to be the current through, through the whole set. I'm just going to label things 1 and 2 to be nice and pretty. Okay, then this is going to split into, come on, stupid pen. All right, this is going to split into I1, which goes on top, and I2, which goes on the bottom. So here we have, now Sydney is trying to lick the pen. All right, no, that's not a, now she's biting the pen. Jesus, Sydney. All right, no, stop it, get down. I'm sorry. All right, so I12, which is the total current, is going to be the current through 1 plus the current through 2. Okay? So current is split. And in the case of capacitors, well, in the case of capacitors or charge split, and that it's a little trickier to see with capacitors, but the same rules apply to charge for a capacitor as apply to current through a resistor. And since current is the rate of charge flow, it's easy to remember that charge splits or whatever's happening to the charge splits. In this case, the current. Maybe that makes sense, maybe it doesn't. Okay. And then we've got an overall voltage change from this point to this point, and that is V. Okay? So we have the same voltage across both, even though the current split. And again, think about your mountain road. This point and this point, you have your two elevations there. It doesn't matter what path you take to get down there. It's still the same height change. You can't change how tall a mountain is by going up a different side of it. Okay, it's all the same. And really, if you go to the mountain road analogy, you can also think about the current as being like cars going down the road. All the cars are coming along down here, and then they get here. There's a fork in the road. Some cars go this way, some cars go this way. Okay, and then when they get down here, they all have to merge again into one road. Here, the cars only have one choice, right? So you got the same rate of cars flowing through for both components, whereas here you have the cars getting split up. But all the cars go the same height change. Okay, so next video I will talk a little bit about how this applies to capacitors and resistors.